Okay, now I'm going to talk you through initially two examples. These are examples done out in detail in the book, but I want to talk you through them, especially if you don't have access to the book. And in this case, I've given a very simple description of the situation, and then I'll talk you through the sketch and the free body diagram. The advantage here being that it's going to be drawn more carefully because it was drawn by professional artists at Pearson rather than me on a tablet. So the first situation is that we have an elevator accelerating upwards, okay? So first we start with our sketch. Our sketch is that there's an elevator that happens to have a person in it, and it's supported by some sort of cable pulling upwards. So we've circled it. We see that the rope enters our circle, so we care about the fact that there is tension in the rope. We don't actually care about the person because the person is part of our object, right? So our object in this case is going to be the elevator plus the person. So again, don't get too confused. If the box of puppies helps remind you, please think about that. And we do have the force of gravity because this is an elevator on Earth. So we have two forces to worry about. So that's step one. The second step is to draw your coordinate system. And again, the book does it this way with X and Y, but note how easy it is to tell the difference between the line that represents X and the forces. So if you think on your picture it isn't very clear that this isn't a force, then please just do it off to the side. So X hat and Y hat, where again that's meant to be up and sideways. So I've done a bad job drawing the coordinate system. Please do better since you're not doing your work on a tablet. So we draw our coordinate system, X and Y. In this case, that's what makes sense. Now, it is true that we only need to worry about one dimension in this case, up and down, but you might want to define your X coordinate anyways. So be careful because there might be some problems that you think are one-dimensional problems that are not. So that's step two, coordinate system. Step three, represent the object as a dot. Boom, there you go, it's a dot. Step four is to draw the vectors. Now, this is where there's a little bit of a back and forth between step 4 and step 5. Gravity, I know, is always down, and tension in this case, remember a few videos ago we learned some rules for different forces. Tension can only pull. All this rope can do is pull up. So the tension force must be up in the direction of the rope, right? A rope can't push. So we know that we have a force up and we know we have a force down. You want to think about their relative magnitude because remember that net force is going to be the vector sum. We know that the elevator is accelerating upwards. So I can say that my acceleration vector must be upwards. And what that means is that my net force must be upwards. So what you want to be careful about is that you don't draw tension and the force of gravity to be the same magnitude because it's not. Tension must be bigger because your net force must be non-zero and must be up. So this is where you have to go back and forth a little bit. If you start by drawing your tension and gravitational forces as equal, you might then look at them and say your net force is zero. But that would be wrong because it's accelerating. So in this case, you have to use your net force knowledge to then make sure that they have relative sizes. It's sometimes tricky to do this. In some situations, you won't always know, and that's okay. Like if you had no idea what your net force was, then maybe you would draw them the same size just because you don't know. But usually you have enough information to figure out something about relative sizes and, in this case, directions as well. Okay, this one is a little more complicated. In this case, we have a skier that's being pulled up a ramp by a rope at a constant speed. So in this case, it's helpful to draw a motion diagram. So we have velocity vectors, and we also denote that the acceleration is zero. Why is the acceleration zero? Well, it's a constant speed. And in this case, because it's a slope, we have a constant direction. Now, this is one of those cases where, going back a video, your mind should say, aha, this is equilibrium, and it is. So this is a situation of equilibrium. So now we draw our picture. We have a person on skis on a slope and a rope, and we identify our forces. So we have a tension from the rope, which must act in the direction of the rope. We have gravity, which is down, because gravity is always down. We have the normal force, which the book uses that notation, which is fine. The normal force must always point perpendicular to the surface. And then we have a kinetic friction force. It's on snow, not ice, so you would assume that there's some kinetic friction that must act parallel to the surface. So we then come over here and draw a free body diagram. Now the book has used X and Y. And again, it's fairly clear what the difference is between the lines that define your coordinate system and the lines that are your vectors. So that should be pretty clear. Now again, I might use slightly different notation than the book on this, but this notation is certainly not wrong. I might call this direction the parallel direction, and this direction the perpendicular direction. And part of why I do that is because there are some problems where you might want to work part of the problem in X and Y, part of the problem in parallel perpendicular. So it's fine if you call one direction X and one direction Y, even if they're not exactly horizontal and vertical, but you must remember that for the rest of the problem. So please, please, please be careful if you do that. So now we come over and we have this tilted coordinate system, and we see that my normal force was perpendicular, so that lies right on one of the axes. The tension force, note that my rope is parallel to my surface, so my tension force is also right on one of the axes directions. And then the frictional force, which is, sorry, that one, the frictional force is also right on one of the axes. But the last thing to think about is gravity, which is straight down. Down now is not one of your directions. So the gravitational force is coming off, it's still straight down, but now there's an angle that it makes with respect to this. And this is where you would have to do a little bit of trigonometry to verify that that angle there is theta. Now the book is telling you that, but if it was up to you, you would have to ensure that that was true. And how you can do this, I'm going to draw the triangles down here rather than making my free body diagram messy. And let me try to use some colors. So this is my X line, this is my Y line. This here is going to be my force of gravity vector. Okay, so far you can see that I have an X and I have one downward thing. This is my theta, right? This is theta. So this angle here is 90 degrees minus theta. And I'm going to quickly run out of color, sorry. But note that this here is 90 degrees. So this angle here must be theta. Why? Again, this was theta, so the other corner of the triangle is 90 minus theta. I have a right angle here, and since this was 90 minus theta, this remaining angle is theta. So that's the trig you do to get to this fact. So the last thing, after you've labeled all of those forces, is F net. Now this is really important and a little trickier in this situation. We have 4 forces here. It is not clear that they cancel out, right? We have forces in basically 4 different directions. Or depending on how you think about it, this one's at an angle and then they're 2 different directions. So it's not trivial to see that these cancel. How do you know that it cancels? Well, because you are at a constant speed, which means acceleration is equal to 0, which means that F net must be equal to 0. So your F net is equal to 0, so you know that these forces, when summed up, must equal 0. You don't know that from looking at your free body diagram. That's hard to just see. But mathematically, it must be true, and maybe you didn't do a perfect job drawing it. That's going to be okay. F net must equal 0 because acceleration equals 0 because you've been told it's at a constant speed. This is an equilibrium problem. So my hope is that this problem is a better example of why you need to do all of the work drawing a good free body diagram. At this point, you might be asked to calculate, for instance, what is the frictional force, or what is the tension? And the only way you're going to be able to do that is if you've identified all 4 of these forces, gotten the right angle, and identified that your net force is 0. And in the next section of videos, we would actually do that type of calculation. So I hope this is clear.